National Center for Quantum Materials at Peck University. So why we are interested in this liquid-liquid phase transition? So if you look at the literature, you will find that there was a large number of materials that have a really interesting property. So they share many different anomalies. For instance, if you look at the melting line, so they have this negative slope melting curve. And also there was kind of extremely the melting lines. And also some of them have this density anomaly and many other kind of anomalies. So for these kind of materials, if I list just some of them, you can see there was a molecular-like system, for instance, water, nitrogen, and also phosphorus. There are some other materials like the semiconductor materials, silicon and germanium, and some of them even is really highly condensed phase and with strong quantum effect, such as hydrogen. And also the transition metals like cerium also share some kind of features with these anomalies. So all of these materials, if you look at them, they're pretty much very, very much different because we have really different chemistry. So we have this molecular system, a semiconductor, and also some of them can be conductor. So the question that we are interested in, is these features, or are these features, they're related, or if they're related, if they're relevant to this liquid-liquid phase transition, and if so, how we can determine this liquid-liquid phase transition, and also the critical point. So in my case, I will just use an example, especially to the study of water, because these the materials that we have the most number of data. So I will use this water as an example to look at how these anomalies relate to this liquid-liquid transition and how we can determine the critical point of that. So here's the outline of my talk. So I will briefly mention the experimental data and have a brief review about the general data that the experiment have, and then propose the question that we are going to ask. And once we propose the model, we'll give you how we can understand these water-like anomalies using the supercritical phenomenon behavior. And finally, because many of this data is related to this liquid-liquid phase transition, and also started in confinement geometries. So therefore, I will give a brief study about the confinement effect and also the surface of chemistry on the liquid-liquid phase transition. Finally, give a brief summary. So why are we interested in water? So there are many kind of reasons that we are interested in water. So here, just list two of them. So the first one, you can see that everybody knows that water is a really important solvent. So it's really important for the study of chemical reactions and also to understand the normal function of biomolecules. So here, it's just two illustrations. For instance, in different states of water, you will see that the materials or the slope looks different. So if you can just look by eye. So here, the left side is the high density water, and the right side is the low density water. So the polymer, if you put it into the water in the two different states, for instance, you can control temperature or you can control the pressure. So you will see that the polymer have a quite different behavior. So in the high density, you can see that the polymer is really like water. Have this chain polymer, but if you put the polymer into the low density water, because we know that the low density water prefer to form tetrahedral structure. So therefore, water does not like polymer. So in this case, the polymer forms a kind of a denatured state to include the volume, the surface water with this water. So the second reason that we're interested is because the water basically have these anomalies that is kind of a prototype for other materials, especially if we compare with the group 4 materials in the chemical table, periodic table. You can see that water can be placed somewhere between copper and silica. So the understanding of this anomalies here for water, basically we can give some indication for the understanding of other materials sharing the same anomalous behavior. So what are the anomalies? So if people really in the field of water, you probably know that there are more than 63 water anomalies that either found by experiment or by computer simulations. There are many of them. So here just list 3 of them. Probably you can quite familiar with them. The first one, of course, is kind of density anomalies. So this was known for more than 400 years ago, but why water has such kind of anomaly, nobody really knows. Even though we have some hypotheses, but we still need to confirm whether or not it's true. So you can say that for simple liquid, it's just as you're going down to lower temperature, so the liquid become heavier and heavier. So that's about, for water, you can see at ambient conditions, so there was a 4 Celsius maximum in the ambient conditions. So this is very different from the simple liquid. So that's also why you can see that the solid ice is floating on top of liquid water. So there are some kind of anomalies that you probably also can heard about that. It's the thermodynamic anomalies. For instance, if you look at the thermodynamic property, for instance, like the specific heat and also the isothermal compressibility. For each of these 2 properties, you can see they can relate to the thermal fluctuations. For instance, for specific heat, is a thermal fluctuation related to the entropy, right? And we know that as you going down to lower and lower temperature, the thermal fluctuation should going down. But you can see compared to water, this is quite opposite. At a temperature higher than 35 Celsius, at ambient conditions, so it's normal liquid. It's going down as you lower and down to low temperature. However, once it crosses to this temperature, so it starts to increase sharply. And similar behavior for compressibility. It's also like, of course, this minimum has at a different temperature, but you can see the behavior. For the simple liquid, it's monotonically going down as you're going down to low temperature. So this is consistent with the thermodynamic relations. But for water, it's opposite. Actually, as you're going down to even lower temperatures, this anomalous behavior becomes more distinct. So this is the experimental data back to 1970s. It's from done by Austin Annual and by Spady. So you can see that as you're going down to the lowest temperature, the non-confined water can access. So it's basically roughly around 240 Kelvin. So this is the lowest data that one can access. If you try to fit in this data near the lowest temperature that you can access, you'll find some kind of power law scaling behavior. So with the fitting temperature, roughly about 228 Kelvin. So the question now is, we know that in the near critical point, you can have this thermal, diverging. It's like a diverging behavior here. So does this mean that there is some kind of a critical phenomenon here? So we don't know yet. So later on, before we go to why this happens, so maybe we take a minute to look at the phase diagram of water. For instance, we know that this is for ambient condition. So just at 1 atmosphere, you can see this is stable water between 0 and 100 Celsius. It can also have this stable liquid. Metastable liquid. It's called superheated liquid above 100 Celsius. If you're going down to lower temperature below 0, we know that it's supposed to become ice. But if you're cooling the system rather slowly and your surface is clean enough, and then you can get this super cool water. So this super cool water can stay in the liquid phase even down to 240 Kelvin. So that's the lower limit the experiment can attack. So below that, so the destination for the liquid is to become ice. So people call this no man's land. And I think it's back to 1980 something, as Mishima found, he did another experiment. So instead of cooling really slowly, what he did is he quenched the liquid really fast from the high temperature side. So in that case, you can cool it down to much lower temperature, for instance, 170 Kelvin. And in this case, we didn't get the ice, but it get amorphous structures called glassy water. And if you melting this glassy water up, you're heating up, so there was 2 destinations. So you can see that there was a regime, so this glass can become ice. Of course, if you're heating too fast, then it become liquid. So this basically, the experimental data that one has for water. And later on that, for this glass water, it's quite new because we don't know that before. And then you can see that if you pressurize, so this ice water down to really high pressure, from 1 bar to 0.5 gigapascal, for instance, you can see that this amorphous water going through a first-order phase transition. So what it sees, you can see that you compressurize, so there was a really sharp transition in terms of volume. So this is just illustration for the low-density amorphous, so the local structure look like ice. And there's another one, it's called high-density amorphous. The structure is not similar to tetrahedral structure. So later on in 92, Peter Paul did some computer simulations. He found something really nice. So in this no man's land, he found some liquid transition, and this line is hypothesized to be the continuous transition from the low density amorphous to the high temperature and the low pressure side, and then terminate at critical point is called the liquid critical point. So people hypothesize that it's maybe because of the exist of this liquid critical point that water have all kind of anomalies. So after that, there was a lot of people, from experiment, from theoretical, from computation. So they want to look at, if this critical point exists or not. So the question is, so this critical point basically located in a no man's land region. So it's below the melting line. It's deeper. It's kind of deep below the melting line. So that's why it's really difficult to detect in terms of liquid phase. So therefore, even though people tried a lot, but still, it's not extremely clear yet. So the experiment did some kind of solutions. What they do is they confine the liquid into a nanostructure. So we know that the lower limit that you can access liquid water is 240 Kelvin in ambient conditions. But if you confine water, for instance, in these nanogeometries, what you access is a much lower temperature. It still can remain liquid. For instance, you can down to 200 kelvins, can still be the liquid phase. This is because these nanogeometries, the confinement effects, stabilize the liquid phase and also kind of avoid crystallization in such kind of system. So let's see what experiment you get by confining water in these nanogeometries. So this is the data that people already had back in the 1970s. You can see that this specific heat is increased really sharply around this 240 Kelvin, or looks like there was a turning point at 227. But if you confine water in this nanogeometry, you found that it's not diverging, but instead there was a crossover, so there was a maximum near this point. And later on, more or less similar times, so people already look at the dynamic property for the system. So what they found is, more or less near similar temperatures, so they found a dynamic crossover. So the point is, whether or not this is related, and if this is linked to the critical point. So here's the question that we are going to ask. Instead, we use because the experiment can only have a limited number of the data. Then what we can do, we can use computer simulations, try to answer the following questions. What happened? Okay, the first question is we're going to answer, try to interpret what happened to the experiment data. So if we look at the data before, it looked like a divergent effect. And then now we confine water into nanogeometries. We saw something is not converging, but diverging, but it's a maximum over here. So we want to look at, why this happens. And second question we want to ask is if this is related to the hypothesized liquid critical point. And if so, and then how we can detect the critical point. So what we want to do is, so here's the deal. So we want to construct a model that basically have two features. So the first one is have to have accessible liquid crude point, because we know that in experiment you cannot. But we can take advantage for the computer simulations. We can build something that have this liquid crude point, and if we have this crude point, then we can look around what really happens near the crude point. So if we get something that is similar to the experiment data, so we can map each other. So therefore we can detect whether or not the crude point exists or not. So for instance, in terms of water, so we can use, because we list several materials at the very beginning of the presentation. So it's not only water, there are a group of materials that shows the liquid, indication of the liquid transition. So therefore we try to take out as much information of water as possible. So we just use a cost-granular models. So for instance, the water, we know that it's one oxygen, two hydrogens with some angles between them. So instead of using this molecular structure, we use some coarse-grained particles to take place in the water molecule. So therefore, we have this one sphere, another sphere, so they interacting with each other through potentials that we're showing over here. So for instance, we know that if you measure the structure information from the liquid water, so here's what you get. So here's the interaction energy between these water molecules at ambient conditions, room temperature. So the gray one. So this is the gray one. So this pink is for the interaction between hydrogen bomb. Because I told you that I not only care about water, but I also care something else. For instance, silicon and germanium, they definitely do not have this hydrogen bond. So therefore, I use something much simpler to simplify this interaction potential by two runs. One is the hard-core interaction. So basically, you can mimic the strong repulsion when the two particles are moving close to each other. And then you have this kind of a weak interaction between two particles. When they at a certain distance, you can stabilize the liquid into one of its minimum. So basically the key feature is, first of all, is the coarse grain. A second, have a spherical symmetric. And the third one is have a two-length scale. So this turns out to be extremely important in your study. So this is the first length scale, and this is the second length scale. So why we think this one possibly have liquid crude point? So if you look at this, the potential that we're going to use, it really looks similar to Lennard-Jones potential. So we know that Lennard-Jones potential basically does not have a liquid. So the reason is, so this one only have for one minimum, so which means you only have a one length scale. So in this case, you only stabilize one liquid phase. But for this potential, because we have two length scales, for instance, if we look at the phase transitions, we can look at the Gibbs energy for the system. Basically, it's the internal energy plus PV minus TS, the entropy term. So if we just use the simplest case, for instance, temperature equals 0, you can see that this is really similar to all potentials because we have two length scales. You can have one here and the other one here. As you changing the pressure, you can gradually switch the stability of these two states. For instance, the low pressures, the low density liquid is stabilized. But if you gradually increase pressure, you can say at some point, these two liquid phases can be equally coexist. And the high pressures, of course, we can stabilize the high density liquid. So therefore, you can see that we have some indication. We are not starting from nothing. So we have some roughly estimation what we can get. So we just run really simple computer simulations, molecular dynamic simulation. You can see that clearly. You can see they coexist of two liquid states. So there's a high density and there's a low density. And if you look at the structure of them, so this is the first shell and the second shell. So they're different by a lot. So for the high density liquid, there are more number of particles, pushing up to the particle, while in the low density liquid, more particles are sitting in the attractive well. So, and if we, if we look back about, think about water, so there was another property for water is have this amorphous structure. So low density amorphous and high density amorphous. And in this model, you can see if you quenching the liquid from high temperatures, we also can end up with the two amorphous state. So this is the low density glass, and then this is the high density glass. And they also different by, structurally different. So in this case, at least, we can show in this model is very, very simple. But you can see this shows, the water kind of properties for this glass-glass transition. So this is, for instance, if you compress the low density glass, compressorize, you can see that it goes through a first order phase transition. It can be a really sharp transition at some point. So this is the final ending point. So you start from this low density amorphous, and then you pressurize in, and you can end up with a really high density amorphous. And these two transitions is kind of a first order phase transition. So if I summarize, I didn't show all of them. I summarize, can try to convince you that this model is simple enough, but it definitely shows the key features that we try to looking at. So first of all, remember that we want to get a model that with the stable liquid-liquid crater point. So here it is. So this is the stable liquid-liquid crater point, and this is the melting line is just above the melting line. So that's why it's stable. Therefore, we can look around what really happens near the crater point and then compare with the experiment. And for this melting line, you can see that we have this is a negative slope. So this is pretty much similar to what is observed in many metal systems. And also we have this kind of a melting extreme along this line. So there was a kink over here. So you have these features. And also we have other water kind of anomalies, such as density maximum. So this is in the PT phase diagram. I just put all of the data over here. So this is the density maximum region. And we also have this minimum region that was later on observed by experiment. So you can see this is the density anomaly region. And we have this low density liquid, high density liquid, and low density amorphous, high density amorphous. So now we have all of this model, and the model have all the features that we want, and then now we can do experiment, what really happens near the crater point. So we will do, first of all, we will do 4 experiments, computer experiment. So first we do one quench, gradually decreasing temperature along constant pressure below the crater point. And we also do another 3 experiments above the crater point. So let's see what happens. So if we first measure the specific heat of the system, you can see that this below the crater point. You can see this is a coexist line. So we probably measure that because coexist line is the first order phase transition. You're supposed to see something like a discontinuity here, but unfortunately it's not. And also above the crater point, so we know that all of the difference between 2 phases disappear near the crater point. So in the one phase region, we probably don't expect to see anything. But you can see what we see something really interesting. So first of all, there's a peak as you're cooling down, in the one phase region. And secondly, so this peak, as you're moving closer and closer to the crater point, so this peak becomes sharper and sharper, okay? And also the position moves, and in the end, it's end up with the crater point. So if we locate all of this maximum to the phase diagram, so we name it called wind line. So this is the response function maximum. Okay, so this means that in the one phase region, according to what we learned from statistical physics, is not supposed to see anything, but we now found some response function maximum, and really can be measured by experiment. Actually, it's not only for this specific heat. There are many other thermodynamic quantities, such as the isotherm compressibility, also shows similar behavior. And then, because experiment also measure the dynamic properties, so I also show you 3 experiments in the computer experiment. First of all, we do one, cooling in the low density liquid, and then we do one heating in the high density liquid. So the third one is we do cooling in the one phase region. Let's look at how these dynamic properties behave. So this orange line is basically for the low density liquid. You can see that this diffuse coefficient gradually decrease as you're going down to lower temperature. And for this, this low density liquid. And then if you look at the high density phase, this is really different from the low density. The dynamic is really different, right? You can see in the high density phase, the diffuse coefficient is lower compared to the low density phase. They separate. But if you look at this one phase regime, what do you expect? So we see that, as at high temperatures, so this line, the green one, basically follows the behavior of low density liquid. And at the low temperatures, it follows the behavior of high density liquid. So there was a kink between these two. And this kink, the temperature where these two behaviors departures is more or less near the Whitman line temperature. Okay? So now we can see that we can tell experiment what exactly you can do to detect the critical point. Okay? You can either looking at the response function maximum, or you can look at this dynamic property crossovers in your system. And then not only that, you can also see the structures shows similar behavior. So we have two ways to define structure. First, we can look at the translational order in the system. For instance, if you're periodical in lattice structure, you get really nice, you can get some behavior for, okay. So this first one, this is the orientational order parameter. You can see we can define this orientational order parameter by this harmonic function. So this is the spherical coordinate theta and phi. So you can look at how it's locally packing near center atoms. So if you, for instance, we do 3 experiments, 1 below and 3 above. So this is really similar to what we see in thermodynamic properties. You can see that as you moving closer and closer to the critical point from the supercritical region. So basically, we call this the supercritical region. And you can see this, first of all, there was a maximum, and second, this maximum becomes sharper and sharper as you move closer and closer to the critical point. So therefore, you can also trace the critical point, so the ending point. So for instance, if you move further, along some line that is really close to the critical point, you should see the structure behavior is divergent. So therefore, you can trace the critical point also by the structure behavior. Okay? And finally, we will give you another example about the response function. It's called the translational order. So before I show you, how this system is locally oriented, and this is long-range order. If there's a long-range order, so you can get this parameter, really different from other one. You can see that as you decreasing the pressure. So this is really far away above the critical point, and this is in the middle, and this is quite close to the critical point. You can see the translational order also shows some indication. So there was some change in the one phase region, and to see clearly, so this is the derivative for the translational order. Similar to the orientation order, you can see that as you're moving closer and closer to the critical point, so this response function becomes sharper and sharper. And until the end, if you're extremely close to the critical point, so this becomes divergent. So therefore, you can see the structure, dynamics, and also thermodynamics. All of the things give you the indication that you can use them to trace the critical point in your system. Now let's compare with all results with experiment. So this is what experiment had before for the nanopore. You can see for specific, there is a maximum over here because there is only one line that an experiment can get. We have no idea which part of the phase diagram they are. And then if we compare to the simulation in all data, because we can search everywhere in all phase diagram, therefore we know what exactly happens in each part of the phase diagram. You can see in the one phase region, actually we didn't see this response function maximum. So therefore, this is definitely not corresponding to the two-state phase. However, in the supercritical region, you can see that we have this specific heat maximum. So this is pretty much similar to what experiment observed. So therefore, we can say that what experiment detect here is more or less in the, for instance, this is a long ending condition. So this is actually in the supercritical region of liquid-liquid water, if there is a liquid-liquid phase transition. And similarly for this self-diffusion, you can see there was a kink over here. So as you changing pressures, so the crossover temperature for this kink also moves. And until if you go to one phase region, there's no kink. So therefore you can, by seeing if there is a kink or no, so you can determine where is the critical point, similar to what we have here. So you can see that, by compare the computer simulations with the experimental result, it shows a lot of similarity of this data corresponding to the supercritical region of the liquid water. So here's the, the real phase diagram that, get from experiments. So before, if you want to look at liquid critical point, so basically in this region, this is really bad region. Why? This is really difficult, really easy to crystallize and so difficult to access in liquid phase. So therefore, it's not a good idea. So according to our study, so instead of looking here, we can look at something that's much easier. For instance, high pressure, lower pressure, and high temperature. For instance, this region, you can, for instance, you can perform cooling study and then look at if there is this response function maximum. So you can perform many of these studies. For instance, you can perform another constant pressure studies and look at, by tracing this maximum, so basically you can, tracing all of these points. So this is basically the response function maximum for this one. And the terminal point, so basically is the liquid critical point. So of course, as I said, not only thermodynamics, you can also use thermodynamics and the structure information to detect this critical point in the system. So by now it looks really nice. It means that, the theoretical study, the experimental observation is kind of a support the exist of a liquid critical point. But there is, so this is, the first experimental study that basically using all theoretical predictions. This is performed by Professor Shu-Sing Chen from MIT. So they basically found something that really similar to what we observed. Okay, so if I give a really brief summary for the first part, is, for instance, this is the real phase diagram that one should know. So before we only know, the coexistent line and the critical point are really important. But actually, in the supercritical region, there's something that is really, really measurable and also can be used to, do something. And so basically, we call this Witten line. So this Witten line, basically, you can be, applied to many different materials to detect the second critical point, even in this highly condensed phase. So in the end, if I have time, I will show you another example. Okay, so by now it seems to be, pretty happy. So we have, we have quite consistent pictures about the liquid transition in water. But there's one thing that I have to remind you that, this is the data from the bulk data. There was no kind of constraint for that. However, this data is from the confined water. So the question is, if this data, if you can map directly the data from confined, nanogeometries directly to the non-confined water. Okay, so this is a really serious question, because if yes, means the liquid critical it is there, and if not, then we have big trouble because we don't know what this data means. Okay, so if we look at these two systems, so basically they're different by additional dimensions. For the bulk case, we know that the properties of bulk water can be controlled by temperature and also pressures, but in the nanogeometries, there was additional dimension. So it's depending on the way that you confine your system. For instance, if you are sandwiching confine your system, so additional dimension is the separation between these two surfaces. So you have one dimension, additional dimension, the separation between these plates. And if you use confinement, finite size confined surfaces. In this case, you can see you have additional dimension. The size of the surface also play a role. And additionally, so we know that if you confine liquid with different surface, the interaction that looks different. If not for all of the liquid, but at least near the surface, it will look different. So later on, in the next section, we'll talk about, how does this, additional parameters that can affect the behavior of the phase transition. And therefore, we can justify if the experimental data is good or not good, or if not, and then which range is good to use. So here's just to give you a brief idea that how we can characterize the surface chemistry of this system. So in all studies, basically we use a parameter called the contact angle, and this contact angle basically is the characterize the interaction between the liquid and the surfaces. For instance, you can turn on some interaction parameters. Here we call this the interaction strength. And if this interaction strength is really small, so means the system is extremely hydrophobic. So you can see the contact angle. And if you, so the contact angle is more than 150. And if this interaction strength is extremely high, so this means, the liquid is just prefer to stay on top of this interface. So therefore, this is extremely hydrophilic. And in the middle is just, between hydrophobic and hydrophilic. So the contact angle basically determined by the profile of this droplet. So you can just make a many, ensemble average and to get a really good estimate for this surface chemistry. Okay, so we study a couple of properties for that. So the first one is we check the surface chemistry. How does this one will affect the density anomaly? So here's how we determine the density anomaly. For instance, for each of these, constant pressures, you can plot the density of the system as a function of the temperature. You can see there's a maximum along each of these pressures. So you can map each of these pressure on this PT phase diagram. So this gives you the density anomaly region. This is the high density, this is the density maximum. You can see that for strongly hydrophobic, so this density anomaly is shrink. First of all, the region is shrink, and secondly, is moved to the lower temperature side. But for the intermediate, this is about contact angle 90, and this contact angle roughly about 0. So this is extremely hydrophilic. So you can see that for these two cases, the density, at least the density anomaly doesn't change much. So this means hydrophobic. So if the confinement surface is hydrophobic, then this is really dangerous. Okay, and then here's the critical point that we determined by the end of the Wiedemann line that I mentioned to you. We can determine by actually here, this one is determined by the compressibility maximum. So you can see that, for different way of confinement, for instance, if you it's extremely confined. 5 or 8 is just less than 5 layers of liquid in between these two plates. You can see the critical point. Just look at the critical pressure. So this is really far off. Okay, so this is a really high pressure, and then of course this for the bulk case as you separating these two plates further and further away. So in the end, the critical point should converge to the non-confined case. So there was you can see that it's more or less around 15. So this is the normalized parameter. So 15 is roughly about 7 to 8 layers of liquid in between, okay? So in this case, so, lower than 15, so the confined data does not overtop. You cannot, leave top of this data on the bulk liquid, okay? But after that, it's more or less okay, at least in terms of this critical point, the critical pressure. We also check, the interplay between confinement and the surface chemistry. You can see that, first of all, you can look at for the highly confined and lessly confined. So they are plotted in the same scale. So for highly confined, of course, it's shifting to high pressure. Okay, and for different surface chemistry, so this is really confined. This is a super hydrophobic, and this is hydrophilic. You can see that hydrophobic is moves to lower temperature and high pressure. So they both play a lot of roles. Okay, so this means the confinement data is not straightforward. You cannot apply directly to on top of this bulk data. So here's the summary for the second part. So for instance, according to the study for this confinement, the surface chemistry and also the confinement dimensions, we know that the phase behavior definitely depend on the confinement. And for hydrophobic confinement, the liquid-liquid transition actually is quite different from the bulk data. And for the hydrophilic confinement, so if the if the confinement is not so severe, for instance, the number of liquid, the layer of liquid in the confined geometry is more than 8, and then probably you are safe. But less than that, the system just changes dramatically. It doesn't look like the bulk liquid. So if we go back to the experimental data, we got this circle, so that was the bulk data, so this is the confinement data. So this have a requirement. So if you want to apply your, load your confinement data on top of this bulk data, so it requires your dimension. For instance, if you were in a nanopore, have to be more than 8 layers, at least according to all studies. Okay? So this put a lot of constraint to the interpretation of the experimental data. Okay, I give so I probably will stop here and give a really brief summary for all of that. So first of all, we basically want to understand the liquid-liquid transition, but it's based on the supercritical phenomena in the liquid phase. We construct a very simple model. This model has all water kind of anomalies. And not only that, it also shows, we take out the hydrogen bond behaviors. So therefore, this is quite a general model. And this model has a very stable liquid-liquid bond, which is really important for the study of this critical phenomena. So therefore, we can explore everywhere in the phase diagram and can compare with experiment. And the second one, we according to all study, because this model is not water, so we cannot call it water because there was no hydrogen inside. And also there are some other difference I didn't tell you exactly, but it shows all water kind of anomalies. So this means, the water kind of anomalies may not be due to the hydrogen bond, okay? And may also not due to the tetrahedral liquid, because we know from experiment that water, silicon, germanium, so they all share similar anomalous behavior. And the other thing they're similar is their structure. This stable structure is tetrahedral structure. But according to all study, because all model, the stable structure is FCC structure. So therefore, it also may not be due to this tetrahedral structure for this anomalous behavior. But there was a key message here, is all of this anomalous behavior maybe because the existence of two-length scale. This may be kind of ambitious, but I think that's the conclusion that basically we can get from our model study. So it's due to the two-length scales exist in the system. And also we propose the concept of the Witten line, and then we can use this Witten as in the supercritical regime, and we can use these Witten lines by tracing the Witten line ending point, basically giving you the critical point. So you can use this one to detect the critical point. Actually, it's quite successful in the study of liquid water for experiment. And finally, I will not show you the details, but just give you a finalized structure pictures. So actually, the concept of the Witten line or the supercritical phenomena is we first observed in this classical system. Actually, it can also be applied to really condensed system, because we know hydrogen is the smallest atom that we know, and they have a strong quantum effect in that. And we basically studied this what happens to the liquid-liquid phase transition in hydrogen using this quantum dynamics. And we found exactly the similar behavior as what we see in the classical system. So you can see that this is the conductivity of the system. So as you move closer and closer to the critical point, the conductivity becomes sharper and sharper. It's a continuous because there is a maximum here. And also the response function becomes, there is a maximum over here. And secondly, you can also look at the fraction of the hydrogen atoms and also the fraction of hydrogen molecules, because the hydrogen atom is the contribute to the conductivity, while molecules can be insulating system. You can see that this structure also gives you the information that the exist of this Witten line here. So by tracing the ending point for all of these response functions, basically we can also detect the liquid corresponding hydrogen, because we know that from experiment, so the exist of this the critical point is at really high pressure, and then this many kind of more than 100 gigapascal is too difficult for experiment to go to that regime. So therefore, what we propose, instead of looking at this really difficult regime, so you can look at something at higher pressure and lower pressure and high temperature side. It's much easier. So therefore, you can treat the critical point. Okay, finally, I will give acknowledgement to my collaborators and also to acknowledge the support from these three resources. Thank you for your attention.
Thank you very much. Let me open to a very short discussion. Question.
So this is a very good question, because I don't know about experiment. In all systems, we know clearly, which part is the low density light, which part is the high density light. So for instance, if you look at, not sure if I can. Yeah. So yeah, you can see that this data that we get. So this is for the this is purely low density phase. This is in the 2-state phase, and then you can see there was no crossover, right? But if you look at this green one, it's basically in the supercritical region. So clearly there was a kind of a kink over here, and you can see the data is a departure from this low density liquid at some point. So I don't think it's it's a need to be clarified, because the data tells everything. Okay, this is a really good question. I think the structure makes a lot of difference. So if you remember the structure of the system, for instance, the orientational structure and also the translational structures, it has some behavior at one side, a high temperature side, and also shows another behavior in the low temperature side. So I believe that is due to the structure, because you can form kind of a local packing, and this local packing definitely will affect the dynamic properties of the system. Yeah.
I ask a short question. You mentioned about dependence, your results on so-called low crossover dimensionality, which means that you have different shape of confinement, so say cylindric core and slit light. For cylindric, you will have larger shift. Did you receive experimental results or continuous simulation results for this concept?
So we compare with the experimental data is for the nanotube. It's one-dimensional nanotube, and all data actually is 2D confined. We just confined within the sandwich. Yeah. But I believe that they should share the similar features. We probably will move, we probably will do another test for this nanopore confinement. Yeah. But of course, we didn't see too much, strange confinement, because that definitely will affect the phase behavior.
And what maximum shift of temperature phase contribution did you receive?
Can you repeat?
What is the value of temperature shift?
You mean in terms of the real unit?
Yeah.
So this is a good question, because we use this cost grain model. So I actually didn't compare the real number. I only can tell that it's how many layers of liquid that is safe for you to draw the conclusion for this confinement data. Yeah.
Thank you very much.
Yeah. Thanks.
As I told all of you are invited to go downstairs to the entrance of our building and take common water. let us do it.